Hello students. Now we are going to start the descriptive chemistry unit. It is going to be divided into 3 parts. Let's start with the first one. We will talk about atomic structure and periodic table, periodic properties of chemical elements, and finally electronic configuration and hybridization.
If we have a look at the structure of an atom, we can see that in its nucleus we can find the protons and neutrons, whereas on the orbitals we can find the quantic numbers. The quantic numbers can describe an electron in an atom completely through the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and lastly the spin quantum number. In this next slide, you can see the periodic table. In this table, you have the different groups of elements organized. In the first case, you can see metals, which is the purple color, semi-metals, non-metals, and noble gases, which will be found in the group 18, which is the one on the right. Now, depending on where they are found in the periodic table, they will have different oxidation states. For example, the group 1 found on the left of the periodic table will have an oxidation state of +1. The group 2 will have an oxidation state +2. But it gets a bit more complicated. When we're going into the group 13, the oxidation state can be +1 or +3. In group 14, it can be +2 or +4. In group 15, it can be +5 and also -3 and +3. Now for group 16, it can be either -2, +4, and +6. For group 17, the oxidation state can be -1, +1, +3, +5, +7. But the most important thing is to remember that for group 18, which are noble gases, the oxidation state is 0. Quantum numbers often describe specifically the energy levels of electrons in atoms. In this periodic table, we can see how the first 2 groups correspond to the letter S, and then the groups from 3 to 12 letter D, 13 till 18 letter P, and then we have the F block, which is barely going to be used. To take into consideration the electron configuration, we need to look at the periodicity, which is what we talked in the last slide, but also Coulomb's law, which takes into consideration the first ionization energy, the atomic and ionic radius, the electronegativity, and the typical ionic charge. The electron configuration can also be determined by the Aufbau principle. That means, when we look at an atom, the first electron that is going to be covered is 1s. After that comes 2s, then 2p, and so on and so on. Having a look at this slide, we can get a lot of information that comes from the periodic table. For example, the atom radius decreases from the top part to the bottom part, but also from the right part to the left part. As for electron affinity and ionization energy, it is exactly the opposite. It increases from the bottom part to the top part and also from left to right. Now let's have a look at the electron configuration. Each orbital, which is an energetic level, can have a maximum of 2 electrons. We have the principal quantic number, which is found in the letter N, and it can either be 1, 2, 3, etc., and it represents the level or layer. The quantic number of angular momentum can either be 0, 1, 2. It is represented by the letter L and is n-1. Let's say L equals 0. That means we have the principal quantic number S. If we had P, which would be 3 orbitals and a maximum of 6 electrons, we would have L equals 1. and so on and so on. To look at the magnetic quantic number, which is m, that is from minus L to plus L, going through -2, -1, 0, etc. And the spin quantic number, which is S, can either be -half or +half. In this next slide, we can see two different principles or rules. The first one is Pauli's exclusion principle, which tells us that two or more electrons cannot be found in the same quantum state within a quantum system at the same time. As for Hund's rule, it tells us the electrons at the beginning take place in orbitals with an identical energy, unpaired. That means they're parallel spins. Later on, they will change, and they will not be parallel anymore. Let's have a look at the first example. In this case, we have fluorine. Its atomic number, Z, is 9. We need to know how many sublevels or layers are going to be filled. If we start with the sublevel S, the first one is 1s, so we're going to put 2 electrons in there. The next one should be 2s, so we're going to put 2 electrons there as well. As for the next sublevel, we have P, that is 2p. So we're going to fill 2 electrons, but then we only have 1 left, because the atomic number is 9. That means that the electronic configuration in this case for the fluorine, it's 1s to the power of 2. That indicates that we have 2 electrons in that sublevel, 2s to the power of 2, and 2p to the power of 5. The number of electrons in the last layer, in this case 2s2 and 2p5, would be the valence electrons. In this case, it's 7 electrons. Have a look at the example number 2 and try to do it by yourselves and see if you get the same result. The p orbitals can have 3 orbitals, which is a maximum of 6 electrons. They are axis-oriented, X, Y, and Z, and the 3 of them need to have the same energy. In order to create covalent bonds by hybridization, we can combine the pure atomic orbitals to generate hybrid orbitals. The hybrid orbitals are a result of an addition or subtraction to describe 2 or more atomic orbitals. Let's have a look at an example. In this case, we have methane. Methane can be found in a fundamental state. In that case, it has the box of 2s with 2 arrows, each one pointing in a different direction, and then 2p with 3 different boxes, and then 1 arrow in each box pointing to the top part. Now, this is done because every time we have different electrons, they fill up all the boxes, so each one of the boxes, and then, in each sublevel. And then, once all the boxes are full, we start to fill each one of the boxes again, but with the arrow pointing the other side, as we can see in 2s. Now, when it is excited, we're found in an excited state, the arrows are all full, they're all single, so not one of them is paired, and we can see that all of them are full. And then, in the last case, we have the hybridization. In the next slide, we have different hybrid orbitals. This is just an example, and we can see the different degrees, the different angles, and how the molecules are found. They can have different geometries. It can either be linear, it can be trigonal flat, it can be a bipyramid trigonal geometry, octahedral. They're all found in the slides that you have. I don't feel like we should stop and spend much time looking at them, but it is curious and it's important to know.